Well, Chris, back for a second talk at the event. So, sterling work, Chris. Over to you.
Thank you, Chris. Yeah, thanks everyone. Appreciate your time this morning, and a huge thanks, as I said yesterday, to everybody involved in the conference, the organisers, the volunteers, caterers, AV crew. It takes a lot of effort to put on an event like this, and it's been fantastic. Yeah, so if you came yesterday hoping to see this talk and sat through a talk you didn't expect to see, I appreciate that, and I appreciate you coming back to hear this one. The topic is, experiences scaling a modular monolith to microservices using the 4+1 views. So just to sort of, I guess, help me understand what you're expecting out of today, who's here because they're currently dealing with something that looks a bit like that? Yeah, only one person, yeah, a couple of hands. Or I think a lot of us have dealt with systems that we would characterize in this way. Who's here because they started with something like this and they turned it into something beautiful like that. And then they did this and then they got that. Yeah. This is, I think this talk is about, I use monoliths and microservices in the title, but the reality is what I hope to achieve by the end of this talk is to convince you to stop using those words altogether. I think they've become kind of meaningless in our industry. And I want to give you a more nuanced language to discuss systems and mental models for thinking about systems. Big Ball of Mud, actually, I love this. There's a paper about it, did you know? Called Big Ball of Mud. And I love just the opening line. While much attention has been focused on high-level software architectural patterns, what is in effect the de facto standard software architecture is seldom discussed. This paper examines the most frequently deployed architecture, the Big Ball of Mud. And this was in, when was it? 97. We've come so far, haven't we? So before we get into what are the 4+1 views and how it works, does anyone remember this show? Yep, Drew Carey, whose line is it anyway? Do you remember his catchphrase?
Whose line is it anyway?
Well, close. You say, the rules are all made up and the points don't matter. And I think this is something to keep in mind. You know, software architecture patterns and principles, they're not discovered in the wild. We create them, we construct them. They're things that worked for someone in a context and they wrote about it and other people looked at it and thought, I'll give that a try. And then over time it becomes, this is how you must, this is the rules of building systems and so on. But ultimately what they are is they're models. They're mental models for how to think about, how to plan, how to design systems. And just like this model of the solar system, they're often quite wrong, but they might be useful. George Box said, all models are wrong, but some are useful. This one was quite useful for helping people understand that the Earth is not at the center of the solar system. It's quite useless if you're trying to plan a spaceship trip to Mars. And I think a lot of our mental models for software are a little bit more like this than they perhaps could be. So this is an example of how people sometimes draw software architecture. Have you seen a diagram that this reminds them of? It's got some boxes, got some lines. Just take a minute and think, like, what does this tell you about the system? Much? I mean, it's kind of a setup. It doesn't tell me much. You know, there's lines, they connect to each other. I can't really tell. Does the fact that the boxes are higher or lower mean anything? To the side or to the left or the right mean anything? There's things there that I would expect to be connected that are not, there's no lines between them. There's things that maybe I would not necessarily expect to need to be connected, or it wouldn't be the most important feature of the system, but it's drawn with a big blue line. So this was a question. Someone put this up on Stack Overflow saying, I just did an interview. They asked me to draw a system that looks a bit like Amazon's S3. I'd love to get some feedback on it. So I did share some feedback with the poster. I hope it was useful to them. But I think that this is kind of an example of what motivated the origin of the 4+1 views in the mid-90s. And it's this idea, clarity of communication reflects clarity of thought. And this is going to tie together a few themes throughout this talk about communication and mental models. So while the 4+1 views is a way of documenting and describing architecture, more than that, it's a way of thinking about it. It's a mental model for how to predict what's going to happen and how to think about how your design is playing out. So this is where it started. Again, back in the 90s, this guy, Philip Christian, he was working at a place called Rational Rose. Rational Rose was one of their products. Is anyone who, as Jeff pointed out, old enough to remember when software came in boxes, remember Rational? Yeah, they were kind of, if you don't know them, they were the Atlassian of the 90s until they got bought by IBM and squashed. And they produced a whole bunch of software for helping software developers create software. The version control, diagram modeling, and so on. Grady Bush worked there at the same time and came up with Bush notation, and that evolved into UML, which you may have heard of. Concurrently, Philip proposed this thing called the 4+1 views. And he was trying to react to this sort of fledgling field of software architecture and what he saw as, poor communication going on in the space. So he was looking at diagrams like this and thinking, surely we can do better. Obviously not this exact diagram, but diagrams like this, and saying we can do better. And he drew inspiration from the field of architecture. They don't just draw one diagram. They have front view, side view, isometric view. They're taking one thing and sort of twisting and turning it in their minds to look at it from different perspectives. And he tried to think about what could that look like with what he calls software-intensive systems. So he came up with an approach. He decided that these 4 views plus 1, explain why in a minute, are maybe helpful tools that we could use to think about, document, communicate software architecture. So we're going to talk through each of them in process. So the first half of this talk is basically an explanation, what are the views? And I'm going to share a story of how we use those views to evolve a system over time. So the logical view starts with this statement. The system is decomposed into a set of key abstractions taken mostly from the problem domain. It's 2 really important words there. One is abstractions, the other is domain, problem domain. So if we think about grading things from more abstract to more concrete, we start with the most abstract, we call it the problem domain. A lot of the thinking in this space, it wasn't at the time that he wrote this, but I think the natural successor to some of the techniques he was using in this view is the field of domain-driven design. Is anyone familiar with domain-driven design? Yeah, people? I'm a huge fan of domain-driven design, and this is really, I think, the best technique to use when you're looking at a system through the logical view. So to explain what that means, you start breaking down your problem domain into subdomains. Sometimes people get a bit caught up about what's the difference between a domain and a subdomain, but to be honest, which word you use tells me more about you than it does about the system, because we use the word domain to describe the limits of the knowledge that we're interested in at this point in time, and subdomain to describe breakdowns of that. But your domain might be someone else's subdomain. So it's not like there's a concrete objective definition, this is a domain and this is not. A domain just means a sphere of knowledge, a sphere of undertaking, human activity. And at the point in time that you're building a system, you've put limits around what you're interested in, and that becomes your domain, and smaller breakdowns of that become subdomains. But in that problem area, it's very fuzzy. Sometimes the subdomains are kind of overlapping. You don't get clear and crisp boundaries. You don't get agreement on what actually it should be. And there's a lot of different ways of breaking it down. Fortunately, we don't have time to go into all the different techniques, but if you're interested, domain-driven design is a great place to start learning about how to think about this. We try and translate that into a more concrete mental model, a model of the system still oriented around the domain, but being with more crisp and precise definitions. And we call those things in the DDD world, domain-driven design, I often use DDD, bounded contexts. We wrap a bunch of concepts in a context, we put a crisp, well-defined boundary around it, and we say, the concepts that exist in this bounded context have these precise definitions, and in another context, the same words might mean something else. This is a really helpful tool. Within a bounded context, there's a whole bunch of techniques that DDD gives us to analyze and understand the domain. Event storming is one. People come across this. It's becoming quite popular. Domain storytelling is another one. Or you might just go old school and do entity relationship modeling, depending on the complexity of the domain and how much you want to explore it. But the really important thing here is that none of these things tell you anything yet about the system that you're building. What they tell you about is the logical concepts in the domain, the way that your users and domain experts think about the world. You're trying to break that down into conceptual model, logical, abstract conceptual model. Do not look at these boxes and think, oh, that's going to be a service or that's going to be a class. That's not what we're talking about through this view. We're just thinking, we're looking at the system from a perspective that ignores the concrete reality of it and just thinks about the problems and the mental concept, like the logical concepts that we're dealing with. There's another layer sometimes in there, the concept of a system. And I put that in there to sort of draw attention also to something that you can understand in this view, which is about autonomy. At the top level, at the system level, I say we're dealing with something that's kind of mostly autonomous. It's not ever truly autonomous because you probably have dependencies upstream and downstream interacting with other parties. But in the context of the organization that you're working in, this is the highest level of unit that you can think about as a thing. And then right at the very bottom, we have components that are not autonomous at all. They call them aggregates or commands and events or entities. They kind of can't do anything on their own. They rely very much on interactions with other components, other logical concepts to be able to achieve anything useful. And this bounded context layer through this view is quite interesting because that's a really balanced autonomy. Mostly you can think about the stuff happening within it independently, but it kind of still is going to need to work with other components. And you can, if you think about, like in this example, I'm using insurance claiming because that was the system we were working on, like a payments context and a claim approvals context. The claim approvals context, you could think about it, you could implement it, you could change it pretty independently. But of course, it can't fulfill the purpose of the business without communicating with the payments context to say when a payment needs to be made. So we're trying to find a balance between autonomy and interactions. But again, these are logical interactions. It says that interaction, we're not saying whether it's an API call, we're not saying whether it's a message on a queue, we're not saying anything about how the interaction happens. We're just saying that there must be an interaction to achieve the goal of the system, the logical conceptual goal. So that's a lightning fast whip through what a logical view is. As you can imagine, we could spend days discussing and exploring different ways of understanding the logical view, and people do that, and I recommend it. It's quite a lot of fun. The process view, this is where the terms monoliths and microservices starts to come more to the fore, because when we say processes in this view, we're not talking about business processes, we're talking about executable processes. Like if you bring up your process manager on Windows or run top on Linux, you get a list of binary processes. That's what we're talking about in this view, executables. So imagine we're dealing with something that you might think of as a monolith, a .NET application running on a server. One thing that I like about the process view is that it helps us understand that in reality, almost all the systems we work with are distributed systems, even the ones that we think of as monoliths. We're running a process on a server. That's not the whole story, right? You're pushing some code into a browser, that's running in a browser process, and that's making an inter-process communication with your backend server. And you're probably going to push some stuff onto a database, that's an inter-process communication to the database. Sometimes we get a bit narrow in our view of what's a distributed system, and we just think about when we've distributed this one layer of the system. But actually, when you look at all the layers, every system is a distributed system. Probably the only software that isn't is something that is just running on a local machine, saving files to disk, old school Microsoft Word before it was cloudified. So most of the systems probably many of us are working with are genuinely distributed systems, even if we think of them as monolith. And the purpose of the process view is to help you understand the system through that perspective and to think about and reason about the kinds of problems that arise with inter-process communications and scaling and so on. Because in reality, that single monolith probably scaled out. So you've actually got 10 or more or 100 runtime processes operating in parallel. You might have a couple of load balancers, more executable processes executing your system with inter-process communication. Every user is running a separate process in their browser, and maybe you've got a scaled out read replica in your database layer. So this view is about helping us understand what's going on from this perspective. What are all of the executable processes? What processes are talking to each other? What kind of inter-process communications do we need to worry about? And it's helpful because then we can think about what are the units of tactical control? What can we start and stop independently? What can we scale out independently? What can we configure independently? What can fail independently? What can go offline? And those inter-process communications become points where we have to think about those sorts of failure modes. So we've moved from the logical view, which is all about the problem space and the domain and the logical understanding of our users and the way they think about the world, to a more concrete view, looking at the runtime components, the executables. So let's think about microservices for a moment. It's in the title, we've got to talk about it. So this is the principles of microservices as outlined by Sam Newman. And these principles are quite interesting and helpful, and you maybe start to see that a couple of them align with some of the views that we've been talking about. This one in particular, the principle that a microservice should be modeled around the business domain suggests to it that the logical view has something to tell us about how to fulfill that principle. And this one down here about deploy independently and isolate failure, although I haven't articulated it here, is kind of aligned with the process view. So we can start to see that these views gives us different ways of thinking about some of these different principles if we're trying to do microservices. So one interesting thing now that we've got these two views is much like we can sort of move around a building and see it from different perspectives, we can sort of rotate the system in our minds and think about, okay, well, if we're thinking about the logical concepts from the logical view, how do they map onto the processes in the process view? And one option is that we just stuff all the logical concepts into one process. And that's kind of what I think a lot of people think of as a monolith, where you have everything in one. You may or may not have neat boundaries between these logical concepts, and we'll talk about that a bit more in a minute. There's another option, which is that you create a runtime process per bounded context, which I think is kind of the intention that the people introducing microservices had when they said modeled around the domain. But they don't specifically say what level of abstraction, just that it does align with domain concepts. So one idea is you can take that abstraction level of the bounded context and say one process per bounded context. Or you can do what a lot of people do when they get really hardcore microservices and go, actually, we're going to do nano services or tiny little services. But what they've ended up doing, especially if they haven't considered the logical view, is creating multiple processes per bounded context. And you remember what I said about autonomy? The autonomy is defined by the components that need to interact as indicated in the logical view, and then you spread them out across processes. They're going to need to interact. So now you have a lot more inter-process communication. So what does that mean? Well, it means you get situations like this. Everyone remember these articles that came out a couple of months ago? Amazon, it just took the web by storm. Amazon, you know, the poster child for microservices is giving up. They're throwing serverless under a bus. Monoliths are sexy again. Love it. It was just, it was a beautiful storm in a teacup. But this was the actual blog post. And when you read what they said they scaled up the prime audio video monitoring service, reducing costs. And I think that this framework of looking at the logical and the process views helps you understand what was really going on there. Because what they had done was over-distributed their service. They only were managing one bounded context, really, the monitoring one. And then what they did is they brought it back into one bounded context for a process. And all of a sudden, the cost went down, which was great. But it wasn't a monolith in the sense that, you know, we would understand it when we look at the whole system, because there were also a streaming service, an account service, and probably a dozen other services that this team had nothing to do with. So what does monolith and microservice even mean there? I think that what people have kind of started doing is they're saying it's a monolith if I can identify things that I could have separated but chose not to, and it's a microservice if I can see things that I could have put together and chose to distribute. But that's such a relativistic term, right? Like there's no concrete definition of it. So that's why I started by saying I don't think these terms are that useful. I'd rather be more specific and precise and talk about runtime processes and logical concepts like bounded context and how we're mapping between them. So some symptoms that happen when you have either not understood your logical view very well, or certainly not represented it or aligned it in your process view, you get a lot of inter-process coupling. You get poor performance, more inter-process communications, higher latency. And there's some common workarounds that people introduce when this happens. Things like caching or more powerful hardware and networks. That was exactly what the Amazon Prime audio video monitoring service team were dealing with. You've got availability risk, more points of failure to complete a domain operation. Because if your domain operation is encapsulated in a component in your logical view, then you've spread it out across a bunch of runtime processes, you've got more availability risk. Any one of those processes fails and you can't complete the domain operation. So what do people do? They put in place circuit breakers, bulkheads. So you've heard of these patterns, and they're trying to protect components from other components failing. Doesn't necessarily mean that you can complete the operation, but then you just need to spend more time thinking about, you know, alternative pathways for the user to complete their journey if a certain component is down. And all these problems go away if you just align the process view components with your logical view component. And the last one is sometimes you have challenges deploying independently, and a common workaround for that is consumer-driven contract testing. Now, I do like consumer-driven contract testing, but I do often consider teams thinking that it's necessary to be a symptom of a misaligned logical and process view, or more accurately, a completely unconsidered logical view, because teams drive straight into the process view without having done any of that domain analysis or domain modeling. One important type of process to consider is our boundary processes, because at the boundary of your system, other parties are interacting with you, and of necessity, they have to interact with one process because they're connecting to one piece of software. But that process needs to represent a lot of concepts usually. And so the two typical examples are the UI and the API, like an integration API where third parties are connecting to. And so by necessity, these processes have to be a process that has multiple bounded context represented within them. Is that a monolith? I mean, maybe, probably not, because you've probably got other components, other runtime processes that have got elements of those bounded contexts represented within them as well. We'll come back to this in a minute after exploring some of the other views. One thing to consider with that, though, is you've got bounded context A and bounded context B, and I just said don't distribute them around your processes. But when you look at this view, going back to that sort of UI backend database view, you can't help but distribute your bounded context between those processes. The processes must be separated because they have to run in different locations. One has to run on the client, one has to run on a server that has high CPU, and one has to run on a server that has high I/O, input/output. So we're going to come back to that in the physical view, but I just want to draw attention to the fact that this kind of distribution is necessary and you should optimize around it, versus this kind of distribution is maybe not necessary and is going to cause you a lot more problems than you necessarily need. Or this kind of distribution, which is the total misalignment of logical concepts and runtime processes. So this kind of distribution is necessary and good, and we'll see why in the physical view. This kind of distribution is probably going to lead to more problems than it's worth. That's the process view. Let's talk about the physical view, which I've kind of started alluding to. The physical view is about the hardware. The software has to execute on hardware, on some computers. We can map processes onto these execution nodes. This is getting interesting because there's an example scenario that really highlights how arbitrary the mapping of processes to runtime nodes is. And this is where we run all of the processes in the whole system, no matter how distributed it is, on one piece of hardware. So when do we do that? Everyone does it when we're developing the system. Sorry? Well, that's when a single page app is running in the browser, but it's probably connecting to another process running in the back end. I'm thinking more about it at dev time. So at dev time, you've got one computer that's running the UI, it's running the back end, and it's running the database. So all those processes are on one physical piece of hardware. Single page app, you've deployed one process out to another piece of hardware, which is your client's machine. Or if you're doing development on it, it's probably running on your machine. So you've got this, it becomes quite clear when you think about the dev time experience that processes can be distributed across hardware or physical hardware, or they can be collapsed down onto one. So maybe when you deploy into an environment, this is like an Amazon diagram, you might have a scale out compute capability with a load balancer and a separated RDS or some sort of database service, and then of course the client's computer. And then we can map the processes in this environment to the execution points that they have to run at. So the key principles for designing how to map the processes or to design your physical nodes are about locality, like where does the hardware need to run? This is why things like the edge are important, because we're saying it needs to run at the edge. The UI needs to run at the client side usually. Even if it's a thin client, there's some code being pushed out and executing on that machine. Hardware characteristics like CPU, RAM, I/O, that's usually the reason to separate your database from your application. But in the early days, maybe just run your database on the same server as your application if you don't have some of these requirements. Fault isolation is another one where sometimes the hardware is the cause of the fault and you want to isolate the consequences of that. And that was often a reason given for microservices when it first was proposed. We don't want a hardware failure to take down all the services. So the physical view is, we talked about the logical view, domain modeling, talk about the process view, think about concurrency and scalability and tactical control, starting, stopping, and so on, configuring. And then the physical view is about this, like this hardware execution, CPU, RAM, I/O, networks, and so on. The physical view. So mapping process nodes, we got a lot of options. These are bare metal, tin. We can run processes on physical servers. We've got virtualized machines, EC2 instances, Azure VMs, VMware, whatever. There's an abstraction level there, but the virtual machine is what we consider our processing node for the purposes of where we are deploying our runtime processes to. Docker containers, that becomes the execution environment for the process. It's running in a Docker container. Managed application services like Fargate and so on. These become another execution environment, or even serverless. Serverless, you might think, oh, that's just a process, but it's not. It's actually a process that you're deploying into an execution environment. And the execution environment controls things like the operating system, the RAM, the CPU, the network connectivity, and so on. So the physical view, even in a fully cloudy, serverless world, has a lot of value to add in terms of thinking about these elements of this aspect of the architecture. One thing just to be aware of, though, is that on one side of the line, you can, if you want to, run multiple processes on a single node. Obviously, a physical machine like a laptop or a tin server, you can do that, or a virtual machine, you can do that. You control the operating system. To the right, by virtue of their whole definition, you're kind of limited to one process of yours running in that container, one process running in that serverless function. And even though on the, it's your right, sorry, the more serverless, virtualized layers, you know there's physical hardware underneath it. It's usually not that useful to worry too much about that. So think about the abstraction level, the execution environment for your process. Even when virtualized, that's what we think about in the physical view as being the node that we're diagramming or documenting. So that's at the bottom there, the physical view. So moving on to the development view. This is where we start to see concepts that are coming to be known as socio-technical systems interacting, because the organization structure and various other aspects of how your developers work is an essential part of your system. It's part of the system that you're designing. So how Philip originally proposed it was software is packaged in small chunks, represented by module diagrams showing export and import relationships. That's one layer of it. You might diagram it like this. Maybe it's a .NET assembly or a Node.js package, depending on another one. That's one perspective of the developer view. But there's, as there was in the logical view, lots of layers of abstraction and concretion. We have the same thing in the developer view, because we can also think about disk layout. Maybe you've seen this kind of approach. It's commonly known as ports and adapter or hexagonal architecture, where you group together adapters, which are like the boundary of the system, adapting from inputs coming in, mapping through application services and domain logic, business rules, then flowing through to outbound ports like repositories and data access on one axis of it. So this is really common. A lot of people have been using it for a long time. Another layout that's becoming quite common is this notion of grouping things around the logical concepts, creating a folder for a domain concept and putting all of the code that relates to that in that folder. You're still following the ports and adapter pattern. It's just which view are you using as your principal organizing, as your primary organizing principle. So on the left, we're treating the process view as our primary organizing principle, because the highest level of organization of our code is oriented at things about what's at the boundary of the process, what's inside the process, what's at the other boundary of the process. Whereas on the right side, we're talking about aligning it with the logical view and saying that the highest organizing principle are the logical concepts. And within that, we're then subdividing by boundary, internals, other boundary. So both are actually fine. This one on the right, you might have heard it called vertical slice architecture, if you've come across that term. And it's becoming more popular as people realize that if the domain concept of, say, a comment or a follower changes, I'm going to have to change the database schema, I'm going to have to change the domain model, I'm going to have to change the API validation, I'm going to have to change the UI. All of those changes up and down the stack are cohesive when you think about them as being manifestations of a single logical concept. And they feel really spread out if you think about them as being aligned with the different processes. So a lot of what I'm like the core message that I have here today is thinking about the logical view first and aligning your other views around it is going to probably lead you to oftentimes a better experience than thinking about the process view first and aligning everything around that. I'll keep repeating that message. But not to say that the thing on the left is not still useful. If your domain is really stable, then probably the next requirement you're going to get is, oh, you've got a REST API adapter, now we need a GraphQL one. So implementing that requirement is going to be easier if you've organized around the left principles. Whereas implementing a change to the domain model is going to be easier with the right principles. So it highlights that neither is correct. You have to adapt and evolve over time depending on what are the dominant changes that you're experiencing. So another layer of abstraction in the developer view is our repository layout and organization. And so one option is the mono repo, where we put it all together in one repository. Another is separate repos. Who's working in an environment with repository layout like this, where you've got app in one, backend service in another, and infrastructure in another? Once again, that's aligned around the process view. There's another option, which is to align around the logical view and to have a bounded context per repository. And all of the code aligned with that, whether it's front-end code, back-end code, database code, infrastructure code that supports that bounded context, that logical concept, goes in one repository. So one option aligning with the logical view, another aligning with the process view. I'm not telling you which one is right. Neither is right. You have to choose based on the experience that you have in your system and the kinds of changes you're having. My feeling is that for a lot of people, they're aligned with the process view and they'd probably be better off aligned with the logical view. And if you're having that kind of experience where, okay, we've got this requirement and now the front-end team is waiting for the back-end team, the back-end team has to make a change in this repository and the front-end team has to make a change in this repository and they have to be coordinated, this is a symptom of that. So let's talk about teams, because that's another part of the developer view. The organization of your teams is part of your system architecture. People heard of Conway's law, the idea that the system architecture will evolve to represent the communication pathways in your organization. So the nice thing about 4+1 views is that it puts that organization as a core kind of diagram to document your system architecture. And as part of that, we can think about, okay, maybe we've got multiple teams mapping to a single monorepo. An important principle there is that we should be very explicit about the boundaries within the repository, usually like folder paths, and say, you team, you own team A, you own that folder, team B, you own that folder. But if you want to split it out, that's fine too. And maybe you go down the pathway where you have an app team and a backend team and an infrastructure team. I'm not judging you. I'm kind of judging you. But maybe you go down the pathway where you have a team aligned with a bounded context and a repository for a bounded context. Both are fine. And you can think about now how to map from this developer view through to the process view. And that's basically your CI pipeline, is taking your developer view and producing the process view. So a monorepo compiling to a so-called monolith, it's pretty straightforward, right? It makes a lot of sense. You've got all the code in one spot, you compile it all together, you produce a single runtime binary. Simples. When you split it out into multiple repositories, sometimes people get a bit confused and think, well, then I don't want to have a monolithic runtime process. That's a bad idea. But actually, you can still do that. And maybe, as we've seen, you should be making different decisions about your runtime process architecture versus your developer view architecture versus your logical view architecture. So if you've decided that your runtime process view should be a single monolithic process, but in the developer view, you've decided you'd like to separate the teams and separate the repositories, you should be allowed to do that, and you absolutely can. And you just have to adopt a thing like this, where each of the repositories does a compilation step and produces an artifact, hosted in some sort of package management system, and then a final step brings them all together into the runtime process. There's nothing wrong with this. This works quite well. This is my hot take. Allowing teams to do independent releases via microservices is a workaround for insufficient quality gates on the team modules that could get composed into a monolith. This is what I'm talking about here. So if you're saying we can't do that because one team's going to block another team, think about what that means when that team that would have been blocking the other team is allowed to go straight to production. Who are they blocking then? Your customer, right? Because their stuff's going straight to production, even though it would have been blocking another team. So these decisions, you can be flexible around it. You don't have to be dogmatic. You don't have to just go one way or the other. You should make intentional decisions in each of these views based around the principles that guide the architecture in those views. And if you want to say the process view should be a single process, and you want to say we should have separate teams in the developer view, you're allowed to do that, and this is a way to do that. In the other direction, if you've said we want to have separate processes in the runtime view, in the process view, that's fine too. And if you've got separate repositories, that's simple, just like the single monolithic repository going to a monolithic deployment was simple. But by the same token, it doesn't have to be one-to-one. You can have a single monorepo with path filters on your CI pipelines, producing multiple CI pipelines going to multiple runtime processes. So I just wanted to explore those 4 different options to highlight that the developer view and the process view can be independently designed. And I believe should be independently designed, because you're going to need to change them potentially at different times, and you don't want to be forced to change one at the same time as you change another. So one way of thinking about a monolith, and I use it in, as you can probably see, I have no problems with monoliths when they're well designed. But when people use it as a pejorative, whether it's a distributed monolith like that ball of mud across the microservices architecture that I showed right at the start, or a single process monolith, what I think that is really indicating is that we have a scenario where the boundaries of the logical view are not well represented in the developer view. So this becomes a big ball of mud, or it becomes spaghetti code. This is how we think about it. But what we often don't do is go back and reanalyze our logical view and think about how can we represent those logical concepts in our developer view using the techniques I just described. So again, some symptoms of misalignment there. Inter-team coupling, leading to difficulty making decisions, wasted time, waiting for other teams to complete backlog items. Common workarounds, Scrum of Scrum. Who's done a Scrum of Scrums? Is it like not the worst thing ever? Like, I mean, yeah, anyway. Cross-team planning coordination. I mean, we're striving for autonomy, and we've stuck ourselves by misaligning the true sources of decisions and change with the people that have to execute those changes. Sometimes we have challenges deploying, and I talked about challenges deploying in the process view and talked about consumer-driven contract testing as being the workaround that's often applied. In the developer view, we tend to rely more on process solutions like release trains or cross-team release coordination. And once again, this is not allowing the teams to operate autonomously. And it's kind of a workaround or a reaction to the root cause of misalignment between the logical and process views or developer view without having understood really what's going on. So there's the development view. Scenario use case view. We're going through this quickly. Really, this is the +1. Doesn't add anything. There's no new knowledge in this view. It just kind of takes the other views and highlights some interactions between them. So we might take the process view and try and show how the logical view maps onto it, like a domain operation. We get a command, an aggregate handles it, publishes an event to a queue, it gets handled in a worker process, which writes to the database. So it's kind of taking elements from two views and stitching them together to kind of highlight how they fit together. That's the scenario view. Now we get to the experience report part of this. So this, I've given you now a language to think about, a different language, a different mental model for thinking about systems, these different views and the kinds of decisions you can make in each view independently and how to think about mapping between the views. So we actually used this approach, designing a system over 7 or 8 years, starting in 2015. It's still going. I'm not involved with it anymore. But I'm going to try and tease out some of the key moments in that system journey. As you can imagine, over such a long time, there was a lot more to it than this. But these kind of highlight some of the points I'm trying to make. So when we got started, we started with an analysis of the logical view, and we came up with a bunch of bounded contexts and the interactions between them. Critically, we realized we didn't have to build all of them in one go. We could build just 1 or 2 or 3 for our initial version of the product. And that's because the logical view is the best place to make those decisions because it's about the functionality, about the domain concepts, and you can think about your MVP and what your users are going to experience if you only implement some of these concepts. Ooh, where did that go? Yeah, so then we went to the developer view as a small team, starting a new project. So we just went, well, we're not going to shackle ourselves to having to manage 100 repositories with a small team. 1 repository, monorepo, this will be the way to go for us. But we were very clear about the structure. So we had our multiple bounded contexts, we separated that out into folders. And within each folder, we then had a standard structure for the layout. Now, at the time, we were using the ports and adapter pattern as the primary organizing principle. Hadn't sort of come across the vertical slice organizing principle yet, but I generally these days would favor the vertical slice architecture. In the process view, we did create a distributed system because there were we had a genuine need for 2 processes. We had an API process and a message queue handling process. So these 2 process view requirements necessitated 2 runtime processes. But critically, at this point, we still called them the monolith. We literally called it monolith.api and monolith.endpoint because we represented the bounded context. Each bounded context was in both places. And the handler in the API, like the API controllers in one bounded context would send messages to be handled by the message handlers in the other process aligned with the same bounded context. And then in parallel, the other bounded context was doing the same thing, but they weren't necessarily aware of each other being in the same process. So we had 2 bounded contexts represented in 2 processes, and the 2 processes talking to the same database. And sometimes when I told this to people, they're like, oh, this is terrible, you shouldn't do this. Microservices shouldn't share a database. Like, well, what's the reason for that? It's because of coupling, right? And that coupling comes from the logical view. So if you've got 2 processes that are actually embodiments of the same bounded context, those bounded context components can absolutely talk to the same database because the data belongs to the bounded context from the logical view. So we did have a single database server, and it had 2 separate databases in it, a database for one context and a database for another context, and they didn't mismatch. So in this, that's more looking at the, from the developer view, this is how we produced that process view. We had multiple endpoints that would compile to the separate processes, but they shared a lot of the other libraries and components like the domain models and the handlers and so on. So the physical view, as I said, it was all shared on the same infrastructure. We started with a queue, we had an API running on a server, and we had the message queue handler running on the same server. We were just starting out. It was low load. We wanted to save cost. There was no need to do more. And this is 2015, so it was kind of pre-Docker. So this was kind of the best option for us. But we established some rules because we knew that even though we were starting out in this way, we distributed in the logical view, we had consolidated in all the other views. We had a small team, small infrastructure, minimum number of runtime processes to save cost and save complexity for a small team. But we knew that we were going to probably scale up. So we set some rules in place. One of the rules was inter-context communications only via a message queue. I might think, okay, well, I've got 2 components from different contexts, and I know they're going to be running in the same process, so why can't one just call an interface on the other in memory? Absolutely, you could do that. But as soon as you do that, your design is going to make the assumption that that call is always going to be fast and always going to be available and always going to be synchronous. That locks you in then. Pulling that out of that process is going to leave you in a world where your system expects a real-time, synchronous, highly available, fast call between those bounded contexts. And so when you push them into separate runtime processes, you're probably going to have a bad time. So we started out by saying we're going to put a constraint in place that even though we're deploying these things in the same process to the same hardware for the reasons that make sense in those views, we want to preserve the autonomy from the logical view by making sure that they are independent as they would have to be if they were to run in separate processes. And so this is the first step of that, inter-context communication only via asynchronous message queues. In the developer view, as I showed before, we completely segregated on disk the context so that it was isolated on the disk, and our developers could know which context they were working in. And then we completely segregated the data, as I said, separate databases, but on the same database server. So just to recap the scaling characteristics, in the logical view, we had multiple bounded contexts because of the functional complexity. In the process view, we had a minimal number of processes and no other scaling triggers. In the developer team, single repository, single CI pipeline, everything got deployed at once. And the physical view, shared resources to reduce cost. This, I think, is a really good way to start a project. Reducing costs, reducing complexity for a small number of developers. Eventually, we needed to start pulling some context out, as I signaled that we were going to do that. Pulling context out into separate processes. And the trigger for that was actually not the hardware or anything else. We didn't need to deploy them independently at this point, especially, but they were using queues, and some messages on queues were high priority than others. We didn't want those messages getting clogged up behind other messages on the queue. So we created another queue, and then we pulled out one of the bounded contexts into its own process so we could monitor that queue independently of the other process. But critically, at this point, the logical view was the same. The process view, we had separated out the processes to avoid sharing queues. In the developer view, it was exactly the same. And in the physical view, it was exactly the same. Shared resources to reduce costs. This is an example of what I mean by you can evolve your design in one view independently of the others if you make design decisions that are explicit about the mappings between the views, and you've done a lot of work to understand and think about the logical view in particular. Phase 3, we decided we had more than one team. We decided we did want to have independent deployment. And by this time, Docker containers had become a thing in the .NET world. So we wanted to move into that kind of environment. So we did. We pulled out containers. We gave each bounded context its own container. But we gave each team ownership of some of the bounded contexts, but we still kept it in a monorepository, a monorepo. And we used that path-based filtering to trigger different CI pipelines to trigger the independent deployments. Sorry, is that saying 2 minutes to go? Okay, sorry. All right, I'll zip through this. So scaling characteristics already scaled out, separate processes to simplify independent deployability, multiple teams, single repo, CI pipeline per process, separate clusters in the physical view to allow independent scaling and scheduling by this time. And we wanted to give the team separate operational responsibility for the hardware that they are running. So again, we made different segregation, different scaling decisions in different views based on the characteristics that we needed to at that point in time. So some key lessons learned. Just to recap the rules, intercontext comms by message queue only, segregating on disk, segregating the data. Something we didn't think about was the tests. Because we had a single CI pipeline, we wrote tests that would run in that pipeline. Those tests were end-to-end tests. What this highlighted when we tried to start pulling the context out is that actually your effective unit of deployment is the boundary of your tests. You cannot deploy independent components if they're being tested by a single end-to-end test. So you have to think about, if you're going to do that, how do you modularize the tests so that they can be separated and you can have good isolated per context testing if you want to do per context deployments. Similarly, in the database, even though the applications were tightly segregated, we had hidden access to the database. People doing ad hoc reports, people handling support tickets, and they built up a library of scripts that were doing cross-database joins in violation of our principles. I get why they did it. It was easy to do because it was all on the one server. So that was a risk. So if we'd, with hindsight, if we'd rewritten the rules, we would have also enforced modularization in the tests. We'd have tried to enforce support activities at the context level and treating support tickets that needed to cross context as a red flag that maybe our boundaries weren't quite correct. Reporting is a tricky one. Cross-context reporting kind of always has to happen. I think a data mesh is too big an investment for an early stage team. So I think the pragmatic thing there is to be aware that you're probably going to get some cross-context scripts in the early days if you adopt this approach, and just plan to invest appropriately in separating it when you do need to do the separation. I haven't been able to think of a better way to do that. Some guidance if you're currently dealing with a non-modular system, aka a ball of mud or a traditional legacy monolith. Start with the logical view. Identify your bounded context. Align the developer view with your logical view. Start thinking about the teams and what they own and trying to refactor your code and repository layout to give you that alignment. At the very least, new code should be well aligned with the logical view that you've come up with. Prepare to align the process view with the logical view. Things like queues, segregated data, boundary processes, consider how you're going to deploy those. And only then, if necessary, consider actually deploying separately. You may or may not need to, and it should be the last thing you do. And I think that what a lot of teams do when they're dealing with this kind of thing is they think, oh, as soon as we pull some stuff out of the monolith, our lives will be easier. But if you haven't considered those logical boundaries, you're actually going to make your life harder. So if I really have to sum the whole thing up into one key takeaway, just don't forget about the logical view. It's really, I think, the thing that ties the whole thing together and makes all the rest of the views make sense if you use it as the primary organizing principle in your other views. There are some alternatives that people sometimes ask me about. How does this relate to things like the C4 architecture? People familiar with Simon Brown's C4? You come across it? This is kind of a summary of it. It's actually, I think, complements closely the 4+1 views. It's got some things the 4+1 views doesn't have, like it explicitly talks about the system context. 4+1 views doesn't have a place to specifically talk about the broader context, and I like that about C4. I love that it's simple and you can do diagrams as code. It's missing an explicit logical view. In fact, he's quite explicit about that. I had an interaction with him on Twitter. He got this question: how does the C4 model compare to DDD, domain-driven design, or event modeling? It's a common question. Domain-driven design and event modeling are domain-focused. C4 is technology-focused. They're orthogonal concerns. And I pointed out to him that actually Christian's 4+1 views identifies that the DDD is part of the logical view, but they're not orthogonal because you can project from one onto the other, and you should. And he acknowledged that that's correct. As Philip says, they're not completely orthogonal in the paper due to the traceability between them. And he acknowledges then that you really need all of them to have a complete picture. So while C4 is great, even the author of it says it's not the complete picture. And what's missing? The logical view. Arc42 is another one that people sometimes talk about. It's a much broader framework. There are some elements of it that align with things like the process view and the developer view, but once again, it doesn't have an explicit call out about the logical view. And I think that's a shame. If you're interested in reading more about this, I've got some blog posts about it. That QR code will take you to the entry point. I am in the process of taking a lot of the content from this talk and converting into more long form content. It's not quite there yet. But if you go to that blog post and follow me on the social things, then I'll be announcing when that stuff's ready if you'd like to read more about this topic. And I'm sure I'm over time now, but that is the end finally. Thank you very much.